Good day, I'm Garrett, and today we'll explore how to measure and control the speed of a DC motor using Arduino and Simulink. By the end of this video, you'll see how to build a circuit, log the encoded data, filter the noise, identify the motor model, and implement PI control. Firstly, here are the components you will need. You can see an Arduino Mega. You can use an Uno or any other Arduino as well. Then we have an encoder wire, the motor itself with the encoder on the back, a small breadboard, flyback diode, some jumper cables, a screwdriver, the MOSFET module, and a 12-volt power supply. I'm using a power supply instead of a battery because it's just easier for me at this moment. As we can see with the circuit on the screen, this typical circuit shows the encoder's A and B channels wired to digital pins D2 and D3, while the MOSFET's gate pin is wired to digital pin 5, which is a PWM pin on the Arduino Uno. The motor will be connected to 12 volt through the MOSFET and the flyback diode across the motor's terminals. In my case with Arduino Mega, digital pins 2 all the way through to 13 are all PWM, so I can connect it to any one of those and just set it in software. Okay, I've just updated the circuit on my board, on my PC board, or breadboard, sorry. So as you can see in the sketch of our circuit diagram, we're only using the MOSFET alone, whereas in this circuit, I'm using a MOSFET driver module. So the wiring is a bit different, so the flyback diode is no longer really needed. So if you know, yeah, you can see on this screw terminal, this is V plus and V minus goes to the motor, the motor wires, and on the right side we have a V in and ground, which goes to the battery, goes to the power rail at the back here, and which goes to the 12-volt power supply. And at the bottom, this module has 3 pins that are sticking into the breadboard. The signal, VCC, and ground. The signal pin is connected to digital pin 5 as originally intended. So yeah, a minor change was made, but we're on our way now. Here we can see a basic Simulink model I made for the RPM versus time. Here's 255, with 255 is 100% duty cycle for the Arduino pins. Here's the encoder block with pins 2 and 3 defined. 546 because that's the CPP for this specific encoder according to its datasheet. The time delta, a simple RPM calculation block I made to use the input counts from the encoder to calculate RPM, and a scope and a live RPM reading. Let's see what happens. It should start any minute now. Let's see. So we can see the step response curve. You can see there is a lot of noise. As you can see, the signal is very noisy. So we'll have to apply a little filter, which I'll show you now. Okay, now I've added the filter. As you can see, it's a regular transfer function. The values 1 and 0.0159 and 1. So let's run this and see what happens. Here you can see the new step response. As you can see, it's much smoother than the old one. Here you can see that I use a filtered step data that I ran in MATLAB's Simulink. You can see I named it RPM filter. That's the filter data that was saved into a file. The step in file data that was saved. This is just the PWM signals. So it's 255. You can see And these are the actual values for the step response curve. So using MATLAB's system identification toolbox and this code I pulled off the internet, I was able to compare a first order transfer function model and a second order model and some others you can see here. As you can see, the best fit was 96.21, which is the transfer function number 2, and here it is. Okay, so now for the PI, or the P, PI, and PID controllers. So you can see this is a circuit I set up. It's my previous encoder counts RPM circuit, just with the added PID stuff over here. So firstly, we just commented out the PI and the PID controllers. Now only the PI is active. The P value is 15 in this case. That's what I found works best. I've already played around with this a bit. So yeah, let's see what this response curve is like. Upload any minute now. Let's see. Okay, there we see it has reached steady state. If I hold on to it, you'll see it tries to compensate for it, like so. So that works as intended. And here you can see the current RPM that ran throughout the test. Here's the difference from the subtraction block. This is just for monitoring purposes. But as you will see during that test, the RPM stayed relatively the same or very close to the 100 RPM threshold. Okay, and moving on to the PI controller that I've commented out the P controller. You can see the proportional value is 15 again, because that's what I found works the best. And I set the integral to 7. So let's see how this system works. And remember, this monitor block here shows the current RPM reading. So you can just see how it compares to this with this value, because this value is the difference between the actual RPM and the desired RPM. Let's quickly upload this code and see what happens. Okay, let's see how it reacts. You can see the step response curve for the PI controller. And keep an eye on the RPM. It stays very accurate in comparison to the P controller. The P controller stayed at 90 RPM when I applied force to it or load to the motor. This one compensated correctly for it, and it went a bit over 100 actually. So now to add the differential part. Okay, and now for the PID controller. You see here's the values of 15, 7, and then this time the derivative value is 2. Let's test this circuit and see how it performs. Okay. As you can see, it almost reaches steady state immediately, which is just a bit. If I apply some load to it, you can see it stays relatively close to 100 RPM as well, but it's way smoother than the other controllers. Okay, so as a conclusion to this video, we covered the purpose of this video, the hardware required. We went through a basic PWM RPM control for the motor, and went through 3 different controllers, the P, PI, and PID controllers. And we saw that the PID controller is the smoothest, it has the lowest overshoot, and it reaches steady state the quickest. Thank you for watching.